So this will be a very brief video on the experiment for nylon. I don't know exactly how we're going to number this experiment. It may be experiment 6, sorry, it may be experiment 7, um, or it may be experiment 9. It's unclear at this point of making the lecture video. But the key, what I want to do is I just want to do a very brief analysis of the chemistry that's occurring in this reaction. I don't really want to go into a great level of depth in terms of talking about polymers or synthetic fibers in general. But if you look at the overall repeating unit of this polymer, and these repeating units are denoted by these brackets right here. So if you look at the repeating unit, you're going to see one part of the repeating unit is this hexamethylene diamine. And then the second portion of this repeating unit, is going to be this adipic acid, or this 6-carbon alpha omega diacid. There, or we can just delete it because it's not really that important. Alright, so again, what we need to talk about is how we're going to make this repeating unit of this hexamethylene diamine and adipic acid polymer. So if you think about the overall chemistry that we're talking about here, really the key that we need to be talking about is how do we form these amide bonds, right? Because this is going to be the key reaction, is how do we form these repeating units. So I think that if you're going to talk about amide bonds, you really need to kind of break things down to talking about in general amide bonds. So if you just take a carboxylic acid and an amine, they will not spontaneously form amide bonds. They will not go through the nucleophilic acyl substitution reactions. And the reason for this is that the first reaction that will take place is that you will have an acid-base reaction. The pK of these carboxylic acids are going to be typically somewhere between 4 and 6, and then the pK of the ammonium group that you're going to form here is going to be somewhere between 7 to 8, and so consequently this is just going to be an acid-base reaction. So you're going to form the carboxylate and the ammonium. This cannot act as a nucleophile, and then this is an exceedingly poor nucleophile. Under extreme heating conditions, you can get this reaction to proceed, but not very efficiently. Typically, what is done if you are looking to form an amide bond is that first what you do is you activate the carboxylic acid such that you generate a good strong leaving group here. And then once you form that leaving group, then you can have your nucleophile come in. And that nucleophile can then attack here. You'll get your tetrahedral intermediate that will collapse, and then you'll lose your leaving group. So in the case of an amide, your nucleophile would be a nitrogen. So there are a variety of ways that we can go ahead and activate there are a variety of ways that we can go ahead and activate these carboxylic acids to form leaving groups. The approach that we're going to take in this lab is that we're going to make the acyl chloride. You can also make an NHS ester. This ends up being an outstanding leaving group. And then the most common approach for making activated carboxylic acids is using something called a carbodiimide. And the most popular of these is something called DCC. And so if you get to the peptide coupling reaction portion of your organic chemistry lecture course, you'll talk about peptide coupling reagents and DCC. But again, for this experiment, what we're going to do is we're going to make the acid chlorides, and then we're going to take those acid chlorides and we're going to react those with hexamethylene diamine. So here is going to be the reaction conditions for taking adipic acid, which is this 6-carbon acid, and then we're going to convert it to the diacid chloride in this case. So we're going to use thionyl chloride and DMF in dichloromethane. It's going to be very important that this reaction is done under strict anhydrous conditions. So before we start the reaction, we are going to dry our glassware overnight. The use of DMF allows us to in situ make something called the Vilsmeier reagent. And I'm not going to really go into depth of what the Vilsmeier reagent is, but suffice to say is that thionyl chloride is a strong chlorinating agent on its own, so this can effectively make acid chlorides. The Vilsmeier reagent can make acid chlorides even more efficiently than thionyl chloride. So once we generate this diacid chloride from thionyl chloride and DMF, we are then going to make 2 phases of this reaction, and this is shown here. In one phase, we are going to take our synthesized diacid chloride and put it in dichloromethane. And then in an aqueous phase, we're going to take hexamethylene diamine, which is this molecule shown right here, under basic conditions in water, and then we're going to put that into the top phase. And what's going to be so interesting about this is that it's going to be basic hexamethylene diamine, and that's going to react with adipic acid at the interface of the organic phase and the aqueous phase. And what's so fundamentally interesting about this is that because that reaction is happening at the interface, you will actually be able to control it. That only the reaction occurring at the interface is happening, so you'll get this thin film that we'll take a hook into and we'll start pulling up, and then as we pull up this thin film, you will keep on making a nylon thread at the interface of these two, of the aqueous and organic phase. And so basically, as we keep pulling this nylon thread up, the reaction will keep occurring until we exhaust all of our starting materials in this reaction. So again, a few things to be careful of is that all of the glassware that we're going to be using for the formation of the diacid chloride has to be incredibly clean and incredibly dry. And then the beaker that we're going to be using for actually forming the nylon also has to be incredibly dry. So all of these pieces of glassware need to go into the oven overnight. Because once we add this aqueous phase, we don't want this to be reacting with any of the water to terminate the potential reactivity of this diacid chloride.